All right, so get ready because today we're diving into the world of boosted objects.
And these aren't your everyday average particles?
No, not at all. From what I've seen, this research suggests they could rewrite what we know about the universe.
Absolutely. We're talking potential game changers here.
So we're basically getting a peek behind the curtain of the Large Hadron Collider at the LHC. But before we get too deep, could you give a quick rundown on what the LHC actually does?
Okay, so picture this. It's like a giant supercooled racetrack
Okay.
where protons are smashed together at almost the speed of light.
Wow.
These collisions, they release a massive amount of energy, and that energy, that's where we get a chance to create and study these super heavy particles that usually only exist for like a fraction of a second.
Got it. So high-speed collisions equal boosted objects.
You got it. Think of it like a, well, maybe not a car crash, but more like a cosmic particle collision.
Okay.
And instead of cars, it's W and Z bosons, top quarks, even the Higgs boson.
Yeah, big players.
Exactly. And these particles are already huge, but when they're boosted to these crazy speeds, the stuff they break down into, their decay products, get kind of, well, squished together.
Squish? Like how squished are we talking?
They form this single messy jet of particles in the detector.
A jet.
Yeah, we call it a fat jet.
A fat jet. Okay.
And here's the thing. These fat jets, they can look a lot like the jets from those more common particles, making them super hard to tell apart.
Really? So how do they even start to tell the difference between these boosted object fat jets from all the other stuff flying around?
That's where things get really clever.
Yeah.
They use this technique called subjet analysis.
Subjet analysis.
Basically, imagine taking that fat jet and just taking it apart piece by piece.
So it's like they're doing particle surgery.
That's a great way to put it. By looking at how the energy spread out within the jet, they can actually find these unique patterns.
Patterns like what?
Things like specific energy signatures that could point to a hidden boosted object. They're looking for the particle's, you could say, fingerprint.
Wow, that's pretty amazing. But how do they actually measure those energy scales within the jet? Is there a specific tool they use for this particle surgery?
They use some sophisticated algorithms, and one that's super useful for this kind of work is the Y-splitter.
Splitter, okay.
It helps them pick out those smaller jets, the subjets, inside the fat jet by analyzing the different energy levels.
So they're essentially using a particle magnifying glass to identify the unique energy signature of these massive particles. Incredible. But I'm guessing it's not always that cut and dry, right? I mean, I've seen some stuff about jet grooming. What does that even mean? It's not like particles need a haircut.
Well, not exactly a haircut, but it's close. Imagine trying to study a tennis ball covered in fuzz.
Fuzzy tennis ball. Okay, I'm with you.
You wouldn't get very far. So these jet grooming techniques, things like pruning or trimming, they help to get rid of those pesky low-energy particles.
So it's about getting a clearer view, like wiping away the dust to see what's underneath.
Exactly. By cleaning things up, they can zero in on the jet's core structure and hopefully get a better idea of what that original boosted object might have been.
That makes sense. But even with a clean jet, they still need to know what they're looking for, right?
Right. It's not enough to just see the pieces. You need to know how they fit together.
Exactly. So what do they use as these particle fingerprints? How do they know what patterns to even look for?
So they use these things called event shapes. And they've found that when certain particles decay, say a top quark, the stuff they decay into, it often makes this kind of
way.
a triangular pattern.
A triangle, like a perfect triangle.
Not always perfect, but yeah, a triangle. Like the way the energy is spread out in the jet, it forms this statistically significant triangular shape.
So they're basically piecing together a cosmic crime scene. But instead of chalk outlines, it's like particles and energy. And speaking of detectives, they need to double check their methods, right?
Oh, absolutely. They can't just rely on intuition.
Right, gotta have proof.
And since they can't just recreate these high-energy collisions in a lab.
Because, science.
Exactly. They use these things called Monte Carlo simulations, basically like a virtual particle collider in a computer.
Monte Carlo simulations. Okay, now we're talking. So what are those?
Imagine a virtual particle collider.
Okay.
It lets them test out their theories and analysis techniques in this controlled space. They can smash particles together like millions of times, change up the settings, and see if the results line up with what they see in the real LHC data.
So it's like a test run, but with the ability to rewind and try again.
Pretty much. But, and there's always a but.
There's always catch.
These simulations, they're not perfect.
Of course not.
They're based on what we currently understand about physics, which, let's be honest, still has some gaps.
Yeah, there's always more to learn.
Exactly. So there are always these debates about which models are the most accurate, how much we can really trust them.
It's like they're trying to hit a moving target.
Yeah, kind of. But that's what makes it exciting. They're using the best tools they have, always working to improve them as they get more data, understand more. And of course, the ultimate test is how well these simulations match up with what's coming out of the LHC.
Right, where theory meets reality.
That's
It's
right.
that back and forth that makes this whole field so fascinating. Like they're in a dance with the universe, always pushing to see what's next.
And it's not just about pushing boundaries. There's a bigger purpose here.
Totally. This isn't just for fun, right? So what is it all for? Why go to all this trouble with these boosted objects?
We're talking about the potential to discover totally new physics.
New physics. Okay, now you've got my attention.
Imagine finding particles even heavier than the Higgs boson, or finding a whole new fundamental force.
Wow.
These boosted objects could be the key to figuring out some of the biggest mysteries.
Like what?
Think dark matter, the very early universe, even the nature of space and time.
Now that's a deep dive. We're on the verge of these huge discoveries, and it's these tiny boosted objects leading the way. It's incredible. It's like we're standing on the edge of something huge, right?
And the amazing thing is the LHC is already giving us incredible results.
Really?
Yeah, this whole study of boosted objects, it's still pretty new,
Right.
but it's already shaking things up in particle physics.
So it's not just like theory. We're actually seeing discoveries.
Oh yeah, for sure. And as the LHC keeps collecting data, who knows what we'll find.
It's exciting.
It really is. It's like having this superpowered microscope,
Yeah.
letting us see further and further into how the universe is put together.
It's kind of humbling when you really think about it.
What's that?
All these scientists,
Yeah.
putting so much work into understanding these tiny, tiny pieces of the universe.
It really shows you how powerful human curiosity is,
Yeah,
the ingenuity to figure things out.
absolutely.
And the best part, we're only just getting started.
That's what gets me. We could be on the edge of these massive breakthroughs, and it's all thanks to these tiny little boosted objects.
It just goes to show, sometimes the universe's biggest secrets are hiding in the smallest places.
Well, that's something I'll be thinking about for a while.
I think we all will.
This whole deep dive has been incredible.
Glad you enjoyed it. And remember, this is really just a tiny peek into this world,
Yeah, scratching the surface.
Boosted objects, the search for new physics, it's all out there.
So to everyone listening, if you're curious, don't stop here. Look up the LHC, check out the research. You never know. Maybe you'll be the one to make the next big discovery.
That's right. Never stop asking questions and never stop exploring.
That's all the time we have for today, but we'll see you next time for another deep dive.